Rudrite Research. The frontier made legible. You've seen this 1,000 times. A model reads a few words and has to guess what comes next. It runs them through the model, which scores a probability for every word that could come next. Mat, 80%. Rug, 8. The rest, scraps. So it just picks the top one. Mat. Now here's the leap. Take that same machine and point it at sound instead of text. Slide a window along the wave and ask the very same question: which tiny chunk comes next? Predict, append, repeat. And just like that, the model isn't writing words. It's speaking. So what even is a sound to a computer? Take that wave we just made and hold it still for a second. A microphone doesn't hear music, it just measures. Tens of thousands of times a second, it lays down a ruler, evenly spaced ticks of time. So it's really just a read head sliding along. At every tick, it reads off one number, how high the wave is, right there. Slide to the end, reading as it goes. And that's the whole secret. A voice is nothing but a long list of numbers. But where do those numbers come from? Your voice is really two things working together. First, your vocal cords make a raw, buzzy tone, every pitch all at once. Then the tube of your throat and mouth acts like a filter, a shape that lets some frequencies ring and damps the rest. Multiply the buzz by that shape and the harmonics snap to it. Those bright peaks have a name, formants, and they're what make an ah and ah. Play it through time and out springs the actual speech. So the game never really changes. We just keep measuring pitch, formants, loudness. But here's the problem that defined the whole field. To capture a voice cleanly, you don't measure a few times a second. You measure this many. 24,000 times, every single second, each one a number stacking into a wall. That's what 24 kilohertz means. So a single sentence isn't a few hundred numbers. It's 100,000 of them. Predicting that one sample at a time would take forever. So the whole field found a crack in the wall. Stop predicting raw samples and turn the sound into a picture instead. So how do you turn a wall of numbers into a picture? You stop reading the whole wave at once and you look at it through a tiny window. Drop the window at the start and ask a simple question: how much of each pitch is in here? That answer becomes one column. Slide the window over, another column, again, and again, painting the sound as you go. One more hop and the picture is complete. And look how small it got. The whole second is about 100 columns, not 100,000 numbers. Raw sound is a nightmare to predict head-on. So the first move is to turn it into a picture. Read it like a chart. Time runs across the bottom, pitch climbs up the side, and brighter just means louder. Down the edge we mark the frequencies, low at the bottom, high up top. Now here's the clever part. Your ears don't hear pitch evenly, they hear it logarithmically. So we warp the axis to match, and the frequency ticks slide into place. The lows stretch open, the highs squeeze together. And the payoff is huge. Instead of 24,000 raw numbers a second, the whole picture is about 100 columns. So how do we turn text into this picture? But before any sound, the model has to read, and written text is a mess. Take this line. Start with the abbreviation. We point at DR and spell it out as doctor. Next, the money, written 1,500, becomes $1,500. And here's the trap. 3/4. That forks two ways, a date or a fraction. In a date slot, we pick March 4th. Put it together, and the mess becomes clean spoken words. Writing turns speakable. But even now, the letters still hide their sounds. Look at these three words. Though, through, tough. They all share the same four letters, OUGH. Pull that chunk out, one shared spelling. But listen to what it becomes. In though it's O. In through it's oo. In tough it's uff. Same letters, three totally different sounds. So spelling lies. The classic fix mapped letters to sounds, a step the big models now skip, learning straight from data. So we have the sounds. Now, how do they line up in time? Here's the puzzle at the heart of every TTS system. We build a grid. The phonemes run down the side and the sound frames run across the bottom. So, which sound belongs to which frame? Watch it walk. The first phoneme claims its frames, then the next, tracing a clean diagonal. And the rule is strict. It only moves left to right, never backward. This little ghost haunts the whole field, and every system solves it differently. So how did we do this before neural nets? Start with one waveform. The first idea was simple. Chop real recordings into tiny tiles and glue them back together. Trouble is, the seams click and jump. It's called concatenative, and it sounds natural, but it's stuck in one fixed voice. The other idea went the opposite way. Smear it all into a smooth model, driven by a few knobs, pitch, duration, timbre. That's parametric. Endlessly flexible, but muffled and averaged out. So for decades you got natural or flexible, never both. Neural nets refused that trade-off. So how does a model make sound from nothing? WaveNet's answer was bold. Predict the raw audio itself, one tiny sample at a time. To guess the next sample, it looks back at the samples before it. Reach 2 back, then 4, then 8, doubling the reach each layer. That widening cone is a dilated causal convolution, a long ear over the past. Then it grinds forward, predict a sample, append it, predict the next. But audio runs at 24,000 samples a second, so making 1 second of sound takes far longer than a second to play. Which begs the question, why predict every sample at all when we could predict the picture instead? Tacotron leans on a piece you already know, attention. Picture a grid. The rows are the sounds we want to make, the phonemes. The columns are the audio frames we are filling in. For one phoneme, we score how well it matches every frame, raw numbers at first. Softmax sharpens those scores into a clean distribution, one frame clearly winning. Lift that row up and it is just a little profile of weights. Blend the frames by those weights and you get a single context vector. Do it for the next phoneme and the peak slides right and the next, and a bright diagonal appears on its own. That diagonal is the alignment. Which input am I voicing right now? Tacotron took raw characters and went straight for the picture. Feed in the letters HELLO and lay them against the MEL frames as a grid. A right head starts at the first column, steps to the next, and the next, lighting one cell as it goes. The trail it leaves is that diagonal alignment again. Column by column, it paints the whole MEL picture. So the acoustic model turns text into the MEL, and a separate vocoder turns that MEL into sound. That split, text to MEL, then MEL to wave, defines almost everything that comes after. And it worked, almost too well. Score the speech on a scale of 1 to 5. Tacotron 2 lands at 4.53 and real human speech, 4.58. The gap is only 0.05, basically a tie. Near human, though naturalness is just one of 3 things we care about. But the alignment it leans on is fragile. Sometimes it skips a sound, sometimes it repeats one, and it is slow, crawling out one frame at a time. So what if we didn't generate frame by frame at all? FastSpeech had a sharp answer. Start with the phonemes, the sound units. Then predict up front how many frames each one should last. The length regulator stretches the first phoneme to its length, the next one longer, and so on, laying out the entire timeline before generating a thing. Now every frame slot is already known, so the model fills the whole MEL in one parallel shot, no loop at all. That is 270 times faster than Tacotron. The catch: every reading comes out flat, the same feeling every single time. Fast needs to know how long each sound lasts, so first it has to line the text up against the audio. Think of it as a grid. Phonemes run along the bottom, MEL frames climb the side. Now here's the one rule. The alignment can only ever step right or down. It can never jump backward. So we let dynamic programming score the paths. Frame 1 weighs every phoneme, frame 2 does the same, and the whole table fills up with scores. Then MES picks the single best path, and it locks in, step by step, all the way to the corner. And look what falls out. Count the frames in each column, and that's the duration of every phoneme. So now we have hard duration targets, no attention needed. And this trick, GLOW TTS and VETS both inherit it. So we can predict a MEL. But there's a problem. The same sentence can be said 100 different ways. You could say it faster, higher, more excited, every one of them correct. But a plain model trained to minimize error does the safe thing. It averages them all together, and the average of every lively reading is flat and lifeless. Fast2's fix is the variance adaptor. You just predict the missing pieces directly. Pitch, the melody. Energy, the loudness. And duration, the rhythm. Feed those back in, and the flat line comes alive again. Pitch, energy, duration, a real control surface. And we will come back to these exact dials later. Around the same time, 2 new ways to build the MEL show up. First, GLOW TTS. Its trick is an invertible flow, a network you can run forwards to generate and run exactly backwards to train. And because it borrows MAS for alignment, it never suffers attention errors. The second is GRAD TTS, and it starts from pure noise. Then it denoises, step by step, until a clean MEL emerges. Hold on to both of these because their grandchildren become the modern decoder slot. Up to now we've had 2 separate models, an acoustic model and a vocoder bolted together at a brittle seam. VTS asks, why not just one model with no seam at all? Open it up, and inside there's a posterior encoder, an invertible flow, and a GAN decoder, all trained together. A discriminator keeps it honest, real versus fake. And because there's randomness inside, the very same text comes out slightly different every single time. Natural variation, not a robot. For years, this was the high watermark. But it still couldn't pre-train on the internet or clone a voice from 3 seconds. A new frame was needed. So how do we turn sound into tokens a transformer can actually predict? Take one frame of audio. It is just a vector of numbers. Now keep a codebook, about 1,000 prototype vectors. Scan it, find the closest one, and snap. That frame is now just an index, number 412. One frame, one token. Do it for every frame and the whole waveform becomes a grid of integers, tokens running across time. And this grid is the spine of everything that follows. But one single snap is too coarse, you can actually hear the loss. So next, we stack the snaps. One code is never enough to capture a frame of sound. So here is the trick. Take the vector the encoder just made right here. Line up a codebook of prototypes beside it, and look at how far the closest one misses. That miss is the residual. Snap to the nearest code, and the residual shrinks. Quantize whatever is left, and it shrinks again. And again, each pass shaving the error a little finer. Do this 8 times over, the way InCodec does. So 1 second of audio, 24,000 raw numbers becomes just 75 frames a second times 8 tiny codes. And that is the moment everything turns. The token grid is born. Speech is now a vocabulary. So now we have 3 different ways to hold a voice. The same second of audio in 3 shapes. The raw waveform, the MEL picture, and our fresh stack of tokens. Now watch the data rate. The tokens cost about 600 numbers a second, small and tidy. The MEL is even lighter, near 100, but it still needs a vocoder to become sound. And the raw waveform? 24,000 a second, straight off the chart. So the heavy options fall away, and one of them clearly wins. Discrete is the move. Put the pieces together and you get a neural codec. It is just an encode, quantize, decode pipeline. Sound arrives as a waveform. The encoder squeezes it down. The quantizer snaps it onto codes. And a decoder turns those codes back into sound. Watch one chunk make the whole trip. In through the encoder, snapped at the quantizer, living for a moment as pure tokens, then out through the decoder, and back into a wave. That whole voice is now just 75 frames a second times 8 codes. Lay the output back over the input, and there is almost no loss. But that raises a question. How does the codebook even learn its codes? Here is a sharp question. Should a single token carry what was said or how it sounds? It turns out you want both, split apart. On top sit the semantic tokens pulled from a self-supervised speech model. They are coarse and sparse, the gist of the words, only about 50 a second. Underneath go the acoustic tokens, straight from the codec. These are dense, and they carry the timbre and texture, the real sound. So the plan splits cleanly in two. A language model predicts the sparse semantic line, then a decoder paints in the rich acoustic detail beneath it. Coarse meaning first, fine sound after. So how does the codec actually learn its codes? It is an autoencoder. Sound goes in, gets squeezed down to codes, and a decoder tries to rebuild it. At first, that rebuilt wave comes out plain wrong. So 3 forces pull it into shape. Force 1 is reconstruction. Hold the output wave against the input and make the gap shrink. Force 2 is adversarial. A discriminator guesses real or fake, so the sound has to become believable, not merely close. Force 3 is the quantizer itself, committing each frame to a clean code. But there is a catch hiding in that commit. Picking the nearest code is a hard snap. And you cannot push a gradient back through a hard snap. There's one ugly problem with turning sound into tokens. The encoder spits out a continuous vector, but to make a token you have to snap it onto the nearest code. And a hard snap has no slope, so when the gradient comes back to teach the network, it hits that snap and just dies. So here's the trick. You copy the gradient straight through the snap as if it were never there. 2 gentle pulls keep things honest. A codebook loss tugs the codes toward the encoder, and a commitment loss tugs the encoder toward the codes. Newer models skip the codebook entirely. FSQ just lays down a tiny grid, takes the continuous value, and rounds each dimension to its nearest level. 2 roads, same destination, both turn sound into clean integers. And now we have a frozen vocabulary for sound. In 2023, a model called VALL-E pushed this all the way. First, it turns sound into discrete tokens, just a grid of integers. Then you feed it the text you want spoken, plus a 3-second clip of any voice. And now a transformer does the one thing transformers do. It predicts the next token, then the next, appending each one, looping exactly like writing a sentence. The first codebook runs autoregressive, and the rest fill in parallel. Decode that stream back into sound, and out comes speech in that cloned voice. It was next token prediction trained on 60,000 hours, cloning a voice zero shot from just 3 seconds. Strip VALL-E down and you get a frame you'll see again and again. 3 swappable slots. The codec turns audio into tokens, so feed a clip in. The backbone predicts the next token, the engine in the middle. And the decoder turns tokens back into a wave. Add a little control knob on top, and that's the whole picture. Swap any one slot, and you've got a brand new system. Orpheus is the cleanest version of this idea. It lights up the backbone slot and asks, what if the engine were just a language model? So the codec is snack. The backbone is literally llama 3.23 billion, and it decodes out to a 24 kilohertz wave. But there's a catch. One frame of audio is actually 7 codes stacked together. A language model can only emit 1 token at a time, so those 7 get flattened into a line, 7 steps for a single frame. That's the flattening tax. You pay it on every frame. Now let's grow up the decoder slot. Instead of a plain vocoder, the backbone hands off coarse semantic tokens, and a flow matching network takes over. It starts from pure noise, and learns a straight path that resolves it into a clean mel in just a few steps. Old diffusion wandered there in many tiny steps. Flow goes almost straight. Then a GAN vocoder turns that mel into the final wave. A semantic language model plus a flow decoder, that's the hybrid that defines the modern legends. By 2024, this stopped being one model and became a whole gallery. But look closely, they all share one frame. Light up the backbone slot and just swap what sits inside it. Spark TTS drops in a small quin on a single codec at 16 kHz. Fish swaps to a bigger quin with a fast dual decoder, now at 44 kHz. Higgs goes wider still, trained on 10 million hours, back down at 24. Now keep the backbone and swap the other slot. Light the flow decoder instead. Cozy Voice pairs it with a tidy quantizer, and it streams or runs offline. Index TES adds a GPT in front and dials in emotion and identity. Chatterbox runs a small llama into a flow generator and quietly watermarks every clip. Step back, and every single one is the same frame, with one slot different. Here's a question. Does the model really have to go left to right? The autoregressive way lays down one cell at a time. Each new one waits on the last, so a cursor starts crawling, filling the row step by step by step. But you could also mask the whole row, every cell a blank at once, and predict them all together in a single slam. Then sharpen, refining over a few more passes, the soundstorm and mask GCT idea. Or skip the cells entirely and flow match the whole utterance in one shot like VoiceBox and F5. 3 different paradigms, all sitting in the same frame. Whatever the model decides, the very last box turns a mel back into a wave, and there's a whole zoo of ways to do it. Light up that decoder slot. One mel goes in on the left, one wave comes out on the right. The only real axis here is how many steps it takes. The GAN sits at 1 step and does it in a single flash of a pass. That's Hi-Fi GAN, Big V GAN, Vocos, the whole family. A flow takes a few springy steps instead. And diffusion dawdles through many tiny ones like WaveGrad and DiffWave. Even the old autoregressive vocoders, WaveRNN and WaveGlow, live on this same line. Fast versus natural is just a trade-off in steps. Every arrow that ends in a wave lives right here. So is all of this actually necessary? Meet the counterexample. Cross out the codec. Cross out the language model too. No codec, no backbone, no left to right guessing. The whole heavy stack collapses into one thing. Kokoro. Really just StyleTES2 feeding a small vocoder. And the size? 82 million parameters. Small enough to run on your phone, Trace it back, and it's pure VETS lineage. The lesson? Mastery is knowing when not to reach for the language model. So how do you actually train one of these? Honestly, most of the work is just the data. Stack it up on a log axis where every grid line is 10 times the last. The classic set LJ speech is 24 hours. Libret's jumps to 585. Librelite leaps to 60,000. And Higgs trains on 10 million hours. Remember, this is a log scale, so each bar is a different universe. And that audio isn't free. You record it, segment it, transcribe it, and filter out the junk. It's the fuel, not the engine, but it still needs alignment all over again. So how do you actually train one of these? Start in the decoder slot. The acoustic model is autoregressive. It builds each frame from the ones before it. So during training, we just feed it the real previous frame. That trick is called teacher forcing. And it works beautifully on training data, where the real frame is always sitting right there. But at inference time, it only has its own guesses to lean on. Training and inference drift apart, so you have to slowly wean the model off the crutch. The faster cousin skips the loop completely. It just predicts how long each sound lasts and stretches to fit. Now the very last step, turning that picture into real sound. Take the MEL, push it through a hi-fi GAN generator, and out pours a 24 kHz waveform. But how do you teach a generator to sound real? You hand its output to a pair of discriminators, whose entire job is to shout real or fake. It's the same adversarial machinery as the codec, one fast pass. So how do you train the part that does the talking, the language model on top? That lives in the backbone slot. And the trick is, you don't retrain everything. You freeze the codec completely and leave it fixed. Now line up your data. First, the text you want spoken, chopped by the backbone's own word piece tokenizer, not phonemes. Then, right after it, the audio turned into codec tokens. And here's the quiet brilliance of it. Text and sound become one single sequence. So now you do the most familiar thing in all of machine learning. A read head sweeps along, and at every step it guesses the next token. You score that guess with plain next token cross-entropy. Then you slide forward and do it again. Which means training a voice is just GPT pointed at sound. Freeze, tokenize, predict the next. There's one more part to train, the decoder that paints the final MEL. And it has two rival recipes. Both start from the same place, a tile of pure noise that has to become a clean picture of speech. The first recipe is diffusion. It learns to undo noise one tiny step at a time, nudging its way home. The catch is right there. It takes many small steps, and every single one is another pass through the network. So the rival recipe asks, what if we didn't dawdle? Reset to the same noise, but this time learn one straight arrow, a velocity field that points right at the answer. Flow matching gets there in just a few steps. Either way, both are steered by the language model's tokens. The decoder trains on its own off to the side. At this point, the model can talk, but it doesn't yet talk the way humans like. So we polish it, back in the backbone. First, a round of fine-tuning on really clean data, plus a token that says whose voice and which emotion. Then comes the clever bit, a preference loop called GRPO. Here's how it spins. The model takes a shot. It generates an attempt. And 3 judges grade it. Did it say the right words scored by a speech recognizer? Does it sound like the target speaker by cosine similarity? And does it just sound good from a quality predictor? You add those up, and the total reward flows right back, nudging the model to do better on the next lap. And on the way out, every clip gets an inaudible watermark woven in. Reward what sounds right, then sign it with a mark the codecs can't scrub away. Okay, the model is trained. So how does it actually speak, live? Back in the backbone, it works exactly like a chatbot. You hand it the text and a short voice clip, and it starts a sequence. At each step, it samples one token, with temperature and top P deciding how bold the pick is. Then it just keeps going. Predict a token, stick it on the end. Predict the next, stick it on. Again and again. Append, repeat, forever. Decode that growing stream, and it turns into a waveform. Now there's one trick to make it follow the script tightly. It's called classifier-free guidance. You run the model twice, once paying attention to the text, once ignoring it completely. Then you take the difference and push past it, exaggerating the part the condition added. But notice the cost. This loop is strictly sequential, and a single second of audio needs a lot of tokens. Now the catch. To make 1 second of audio, the model takes a single frame. But that frame isn't one token. It detonates into 7 codes, flattened into a line. And there are about 75 frames every second. So multiply it out. 150, 300, 500 plus model calls for 1 second of sound. Drop that on a real-time meter, and the needle blows past 1x. Slower than real-time. And the thing you actually feel is time to first sound. Sequential decode is the whole battle, and the speed tricks are next. So how do you drag that needle back under 1x? 3 tricks, 1 meter. Start with the problem. 1 token at a time. Put it on the meter, and it sits past 1x, too slow. Trick 1, the delay pattern. Stagger the codebook so they run in parallel, and the needle drops under the line. Trick 2, a dual transformer, 1 heavy body and 1 tiny fast head, and again it drops. Trick 3, go non-auto-regressive, predict the whole thing in 1 pass, and it slams way under. 3 ghost marks, all of them under 1x. Faster than real-time every single way. But here's the relief. You don't wait for the whole clip. The model emits it in chunks. And chunk 1 starts playing the moment it's ready. Watch the playhead scrub through it, while chunk 2 is still being generated behind it. So the number that matters isn't total time, it's first packet latency. Now the second gift. That backbone slot is just a language model, which means the whole serving stack slams in for free. VLLM, KV caching, continuous batching, and paged attention, speculative decoding, quantization, all of it inherited. But something still has to render those tokens into sound. The last mile. So the tokens come out at a steady pace. But they're still tokens, not sound. Something has to decode them, and that decoder forks. Path 1, again. 1 single pass, and the waveform snaps out instantly. Path 2, a flow decoder. It refines step by step by step into a cleaner wave. Now race them. 2 meters. The GAN decodes at 0.3x, blazing. The flow at 0.9x, prettier but slower. Speed lives in 2 places, emitting the tokens and decoding them. So far, the model just predicts sound. But you can also steer it. Remember the variance adapter? It's really a little mixing desk, wired to 1 shared mel. 3 faders, pitch, energy, and duration. Grab pitch and push it up, and the contour steepens, the voice swings higher. Push energy and the whole picture brightens, louder and punchier. Stretch duration and the mel pulls wider, the syllables slow down. Overdrive them and it's exaggerated, underdrive and it goes flat. So these are explicit knobs. But you can also just hand it a reference voice and let it copy. We've cloned the prosody knobs. But could we clone a whole voice with nothing but conditioning? Here's all we get, a single 3-second clip of the target. A style encoder reads it, pulls it apart and blooms it into a bank of global-style tokens, each one weighted. One voice rises to the top. We light up the backbone and inject that blend straight in as conditioning. The output Mel comes out wearing the reference's character. Now push it further. That same clip can set the full identity. Feed it in, and the voice snaps far down the identity axis. The voice is cloned, and not a single weight was touched. Same trick, now for emotion. Picture the voice as a point on two axes. Across, its identity. Up, its emotion. There's the voice, sitting calm. Chatterbox gives you one emotion scalar and a CFG push. Crank it, and yes, the emotion rises, but watch, the identity drifts right along with it. Index TTS2 fixes that. It holds the identity locked and slides emotion straight up, a clean vertical. Two knobs that finally don't fight each other. And the wild part, you can just describe the voice in plain words, warm, slow, low-pitched, and that text drives the very same point. The words become the knob, and every bit of control is just conditioning. Let's trace one sentence through the whole decade. Here it is. Hi, how are you? And here's the rail of eras it has to cross. First, concatenative, splicing recorded chunks, you can hear the seams jolt. Then WaveNet, building the sound one single sample at a time in strict order. Tacotron draws a soft diagonal, learning what lines up with what. Fast predicts the durations and fires the whole mel out in parallel. VTS goes end-to-end, sampling a fresh take every pass. And VALL-E shatters the sound into tokens and just predicts them. Same sentence, a whole decade of transforms, one after another. Every system so far runs one direction, text in, speech out. Moshi breaks that. Here's you. The model speaks, a stream of tokens flowing out. But it also listens, a second stream flowing in at the very same time. Both run at once, full duplex. Its speaking stream stays live even while it's hearing you. Underneath, a roughly 200 millisecond inner monologue keeps it one step ahead. So it can interrupt you and let you interrupt it. Speech stops being playback and becomes a conversation. Here's the last surprise. Put the audio tokens in the middle. That shared band is the hub. Going forward, text flows in and speech comes out. That's the codec language model loop we just built. Now watch. Flip the very same two arrows around. Now speech flows in, tokens in the middle, and text comes out. Same machinery, the arrow just reversed, and that's Whisper. And this reverse pass is exactly how we measure word error rate. So how do we actually know if a voice is any good? We lean on three measures. First, can you understand it? Take the synthesized speech and run it through a speech recognizer, like Whisper. If the transcript comes back clean, the word errors fall, and that means it's intelligible. Second, does it sound natural? We collect opinion scores from 1 to 5. Old Tacotron landed around 4.53, real humans about 4.58, basically a tie. We also run quick A/B preference tests and lean on learned predictors like UTMOS and DNSMOS, so we don't need a crowd every time. And third, does it sound like the target person? We take the reference and the generated clip and measure the cosine similarity between them, often up around 0.91. Together, these three are the whole scorecard. But remember, every one of them is only a proxy for sounds right to a person. Okay, let's put the entire field on one screen. Here's the frame again: codec, backbone, decoder. Every system you've heard of is just a set of choices in those three slots. The biggest family is the autoregressive codec language models. VALL-E, Orpheus, Spark, Fish, Higgs. Then the hybrids, a language model plus flow. Cozy Voice 2, Index TTS2, and Seed TTS. Over here, the masked parallel generators. Mask GCT, Natural Speech 3, F5 TTS, and VoiceBox. And still going strong, the VITS lineage, VETS, Style TTS2, and Kokoro. Dozens of systems, one map. Read any of them as a choice of slots. Let's test the whole framework. Here's the empty frame, and here's a brand new paper from 2026 you've never seen. Just the abstract. A few dense lines of it. Watch the keywords. There they are. Now run a scan across the page. First hit, an RVQ codec, that's the codec slot. Next, a codec language model, that's the backbone. And there, flow matching, that's the decoder. One more knob, a zero-shot voice prompt for cloning. And just like that, the whole system snaps into focus. An RVQ codec LM flow matching system. You just read a 2026 paper in one breath. So here's the whole film in 3 lines. Let's replay the journey on one object. It started as sound, a raw wave. We measured it into numbers, and then we made those numbers discrete into tokens. And that was the unlock. Making audio discrete is what cracked it open. Once audio was tokens, you could point a transformer at it and just predict the next one over and over. That's the second line. Text-to-speech became next token prediction. And every engine that followed folds into one frame, codec, backbone, decoder, 3 slots. So if you remember nothing else, remember this. Audio is tokens, and every voice engine is 3 slots. Here's a normal codec stack. 1 bundle of tokens. And the catch is, everything is jammed together in there. The words, the pitch, who's speaking, even the room. So Naturals 3 asks, what if we pull them apart? Unmix the stack into separate lanes? 1 lane for the content, the actual words. 1 for the prosody, the pitch and energy. 1 for the timbre, who is speaking. And 1 for the fine acoustic detail. Now each attribute lives on its own independent lane. And timbre is special. It collapses down to a single global vector, 1 fingerprint for the voice. So watch what that buys you. Bring in a different voice, swap just that 1 lane, and every word stays exactly the same. Same speech, a brand new voice. In 2022, a model called AudioLM tried something bold. Treat audio itself as a language. First, it lays down a coarse semantic track, the slow skeleton of what's being said. Then it drops down and rattles out the fine acoustic detail, how it actually sounds. 1 language model drives both, just predicting the next token. Then Spear TTS added a twist. Split the job into 2 stages, read, then speak. And here's the payoff. Only the reading stage needs paired data, about 15 minutes of it. Audio had become a language you could learn. Tortoise, also from 2022, took a different road. An autoregressive model proposes the tokens. But instead of trusting 1 guess, it sprays out a whole batch of candidates. Then a scorer called CLVP ranks them all and keeps only the best one. That winner gets handed to a diffusion decoder, which polishes noise into a clean spectrogram, step by step. And out comes the voice. Oversample, then polish. The recipe the field would keep. Here's where it gets wild. Take just 6 seconds of someone speaking. The model squeezes that clip into a single voice print, a compact fingerprint of the voice. And from that one point, it reaches out across languages. Rays fan out, and one by one the languages light up, each speaking in that very same voice. 1 clip in English, out comes 17 languages, all sounding like you. This is XTTS. As these voices get perfect, a harder question shows up. How do you know what's real? Take a piece of AI-generated speech. One defense is proactive. Weave a hidden carrier right into the wave, a watermark called audio seal, a 16-bit payload stamped sample by sample. The other defense is reactive. A detector scans the clip, snaps a bracket onto the synthetic slice, and renders a verdict, real or fake. As the voices get perfect, this stops being optional. For years, talking to a machine meant a relay of 3 separate models. Speech in, recognize, think, then speak. Every hop adds delay, about 5.4 seconds, and somewhere in there your tone gets thrown away. Then the boxes collapse into one, a single model that hears and speaks. The same round trip now takes 320 milliseconds and your tone survives in and out. TTS stops being a component. It's one thing the model does. Here's the quiet payoff of building one machine. The very same trunk, the codec, the backbone, the decoder, does more than read text aloud. Fork it 2 ways. Down one branch is singing, like Diff Singer. Feed it a musical score instead of plain text, and out comes a sung melody, pitch and all. Down the other branch is voice conversion, like KNNVC. Take voice A and a few seconds of voice B. Now grab one little chunk of A, look through B for its nearest match, and snap it in. Do that chunk by chunk, and the words stay exactly the same, only the voice changes. Singing, conversion, plain speech, it all folds back into the one trunk. One toolkit, the whole family. Want to learn more about the AI frontier? Come find us at research.rudrite.com.